In this lecture, we are going to discuss another classical algorithm for distributed mutual exclusion, and we'll also wrap up our discussion of the mutual exclusion topic. The Riccard-Agarwala algorithm that you've seen already for mutual exclusion requires replies from all the processes in the group, which is one of the reasons that it has a high bandwidth. It has a bandwidth that is order n. The key idea in the Maekawa's algorithm, the new algorithm, is that you need to get replies from only some processes in the group, not all the processes, but only some. But you also need to ensure that only one process is given access to the critical section at any point of time, which means that safety is guaranteed. So Maekawa's algorithm works as follows. Each process Pi is associated with a voting set called Vi. The voting set consists of a few other processes from the group. Each process must belong to its own voting set Vi. Now the voting set is not all the other processes in the group, which is essentially the approach of the Riccard-Agarwala algorithm, but the voting set is only a small subset of the group. However, you need to make sure that given any two voting sets Vi and Vj of processes Pi and Pj respectively, the intersection of these two voting sets is non-empty, which means that there is at least one process that belongs to both Vi as well as Vj. So given any pair of voting sets Vi and Vj, you need to make sure that at least one process is in common between those two voting sets. This might sound familiar to you. In fact, it is the same concept or the same idea as quorums, which we have seen elsewhere in the course. However, here the usage of this is slightly different, of course. Now, each voting set is of size k, so all the voting sets are of similar size, and each process contributes by belonging to m other voting sets, including, of course, its own. Maekawa showed that the values of k equals m equals square root of n work best. We'll see a calculation later on in this lecture which calculates why square root of n is a good value. One way of assigning voting sets so that they're always intersecting in any pair of voting sets and so that you get order square root of n voting set sizes is to put all the n processes in a square root of n by square root of n matrix. And wherever a process falls in the matrix, you consider that the processes column, and you also consider that processes row, and all the processes in the column and in the row are together. The union of them is considered to be the voting set of that process at the intersection of that row and the column. So this would result in a voting set size that is 2 times square root of n minus 1, which is still order of square root of n. So let's see an example. So suppose I have 4 processes in the system. Of course, this is a perfect square, so we can put them in a matrix as shown here, P1, P2, P3, P4. And if we select a process's row and column as its voting set, then we get voting sets as shown on the left side of the slide. So consider P1, the process P1, its row consists of the process P1 and P2, and its column consists of the process P1 and P3. So its voting set consists of those 3 processes, P1, P2, and P3, as shown by this circle over here. Similarly, V2, which is the voting set for P2, consists of the processes P1, P2, and P4, and so on and so forth. You'll notice that any pair of processes intersect in at least one, in many cases 2, of the processes in the system. So consider V1 and V4, they intersect in 2 processes, P2 and P3 in the system. So let's see how these voting sets are used then. So first of all, each process requests permission from only its voting set members, not from all, and this is one way in which the Maekawa's algorithm differs from the Riccard-Agarwala algorithm that we've seen previously in the course. Second, each process that is in a voting set gives permission to at most one process at a time, and again this is different from the Riccard-Agarwala algorithm where a process may have given permission to multiple, perhaps all the other processes in the group. Okay, so these are 2 key differences. Anyway, let's look at how the algorithm actually works. So first, initially the state of a given process, and again we describe the algorithm by describing what happens at a given process. The state of a given process is released, which means that currently it is not holding the lock, or it's not in the critical section. Also, its state for voted is false, meaning that it has not yet voted for any other process to get access to the critical section. Now, when this process Pi wants to enter the critical section, it first sets its state to be wanted, meaning it wants to enter the critical section. Then it multicasts a request message to all the processes in its own voting set Vi. Notice that this voting set Vi also includes itself. So when Pi itself receives its own request, it will have to process it. And I'll describe how this processing is done in the next slide. Then the process, after sending out this request message, it waits for a reply or a vote message from all the processes in its own voting set, and that includes a vote from itself. When it has all these votes, it can then set its state to be held and then proceed into the critical section. What happens when a process is done with the critical section? Well, the first thing it does is that it sets its state to be released, again meaning that it's done with the critical section, and then it multicasts a release message to all the processes in its own voting set VI. This is not all that there is to the protocol. Now, when a process PI receives a request from PJ, first it checks if its own state is held, meaning it currently is holding is in the critical section, or if it has voted in the past, meaning its voted variable is true. If either of these conditions is true, then it queues this new request because it means that someone else is in the critical section. Otherwise, it sends a reply or a vote back to PJ, and it sets its voted variable to be true, indicating that it has recently voted. Now, when a process PI receives a release message from process PJ, recall from the previous slide that a release message is received when PJ has just exited the critical section and informs all its voting set members that it has exited the critical section. PI looks at its queue of waiting requests. Remember that PI may be in not just PJ's voting set, but also in the voting set of other processes, and these other processes may be waiting for a vote from PI. But if PI's queue is empty, it means that PI doesn't have any outstanding requests, and so it sets its voted variable to be false and it exits at that point of time. However, if there is something in the queue, then it dequeues the head of the queue, say a process PK. Remember that this means that PK's voting set contains PI, and that PK has previously sent a request to PI which has been queued, and the queuing happened here in the past, right at the top of the slide over here. That's where the queuing happened. And in this case, the entry for PK is dequeued, and a reply message is sent to PK, meaning that PI now has voted for PK to enter the critical section, and so PI sets its voted variable to be true. So why does this algorithm guarantee safety? Well, when a process PI receives replies from all its voting set members VI, including itself, no other process PJ could have received replies from all its voting set members VJ, because VJ would have had intersection with VI in at least one process PK, and PK could have sent only one reply or vote at a time, and it already sent the vote to PI, which means that it could not have voted for PJ as well. Okay, so this means that safety is guaranteed by the Maekawa algorithm. For liveness, a process needs to wait for at most n-1 other processes to finish the critical section, and you might think this guarantees liveness. However, Maekawa's algorithm has a subtle behavior in its original form that can actually violate liveness because it can result in a deadlock. Here is an example of a deadlock. Again, in our example of 4 processes P1, P2, P3, P4, suppose all the 4 processes request access to the critical section. P1 gets some replies but is waiting for P3's reply. P3 in turn is waiting for P4's reply, which is in its voting set. P4 is waiting for P2's reply, and P2 in turn is waiting for P1's reply. Now we've completed a cycle or a circle among these processes, and this is called a deadlock. There is not going to be any more progress in the system because these processes are going to be waiting for these replies forever. So the original Maekawa algorithm, as we've discussed it, is deadlock prone, and these deadlocks can occur. There are of course variants of Maekawa's algorithms that have been published that address this issue and that are free from deadlocks. Returning to the original Maekawa's algorithm, let's analyze its performance. The bandwidth involved in entering the critical section is square root of n messages that you send out to your voting set members, and then square root of n replies that you receive back, so that's 2 times square root of n messages. For exit operation, you're simply sending a reply message to all your voting set members, so that's just square root of n messages. These numbers are better than Ricard and Agarwala's algorithms, which had bandwidths of order n. You might think square root of n is still a large number. It's not constant for sure, but it can be fairly small. So if n is 1,000,000, for instance, then the square root of n value is about 1,000, which is a fairly small number. What about the delays? Well, for the client delay, when no one has access to the critical section, a process comes up and says, hey, I need access to the critical section. It sends out a request to all of its voting set members. That's one message transmission because all these messages are in parallel. And then the responses are received back also in parallel. That's another message latency in the backwards direction. So that's one round trip time. Synchronization delay means that one process is currently in the critical section and one other process is waiting to get in. And at this point of time, the releasing process will send a reply message back to the process PK, which is the common process between the 2 voting sets of the releasing and the waiting process. Then that PK process, which is in common, will forward a vote to the waiting process, which can now enter the critical section. So that's 2 message transmission times one from the releasing process to the common intersection voting member, and then from the voting member to the waiting process. So why is the square root of n the right size for the voting sets in Maekawa's algorithm? Once again, each voting set is of size k. Each process belongs to m other voting sets. Now, the total number of voting set members is k times n, because each of the n processes has k members in its voting set, and so k times n is the total number of voting set members. Of course, because the voting sets overlap and intersect, processes may be repeated in this k times n, but each process belongs to exactly m voting sets, so k times n divided by m should be equal to n, because each process appears exactly m times in this k times n. So k times n divided by m should equal n, and if you evaluate this by cancelling n out on both sides, you get that k equals m, which means that the size of the voting set should equal the number of voting sets that each process is in. Okay, so let's have that equation and hold it to the side. Now consider a process pi, right? So the number of voting sets that are there in the system is equal to pi's own voting set, so that's the plus 1 over here. There are k members in pi's voting set, right? There are k processes, and each of those processes has their own voting set, right? So that's the total number of voting sets that is there in the system. Because each of these k voting set members of pi is involved in m total voting sets, but one of them is pi's own voting set, so the remaining voting sets are simply m minus 1 times k. Okay, so that's the total number of voting sets present in the system. However, the number of voting sets should equal the number of processes in the system, so we have n equaling this value. Now we substitute in the value of m equals k from the earlier equation, and you get n equals k minus 1 times k plus 1. Solving this, you'll see that k equals about a square root of n, give or take a little bit. And this explains why k equals m equals square root of n is the optimal value for minimizing the overhead of k. So in order to minimize k, we set n to be equal to m minus 1 times k plus 1, and then we use the earlier equation k equals m to give us k equals square root of n. Now, the Maekawa's algorithm, of course, does not handle failures. Neither does the ring-based or the centralized algorithm or the Riccard-Agarwala algorithm. Of course, there are fault-tolerant versions of all of these algorithms that exist out there in the literature. Other ways to handle failures include Paxos-like approaches to handle failures. Google's system called Chubby, which is used for locking, is a fairly popular way to handle failures while doing mutual exclusion inside of Google's stack. So Chubby is a system used underneath Google's storage systems such as Bigtable and Megastore. Chubby has not been open source, but the technical details and the design of Chubby has been published in a paper by Google, and that's what we're going to discuss in very brief detail in this slide and the next. Chubby provides only advisory locks. This means that clients must ensure that they access the lock before they access the critical resource or the object itself. So if clients forget to access the lock, then then mutual exclusion may be violated. So this is why this is known as advisory locks. So Chubby, of course, uses a cluster of servers. There are 5 servers by default in the Chubby cell. One of the servers is marked as a master. Again, this is elected using one of the leader election protocols that we have studied before. In this particular figure, server D is a master. Chubby allows clients to not only do locking but also write small configuration files. And Chubby relies on the Paxos consensus algorithm. Chubby again is a group of servers with one elected as the master. The other servers in the group, the non-master servers, are just slaves. They replicate the same information as the master. When a client wants to read one of these small configuration files or the lock file, it sends a read request to the master, which can serve it locally. Okay, so the master serves all the requests locally. When a client wants to write, however, it sends a write request to the master, which then forwards it to all the servers in the group. It then gets a majority of them to respond back to the master. When a majority of them respond back, you reach a quorum in the system. Then the master can send back a response to the client acknowledging that the write has been done. Okay, so this is where mutual exclusion comes into play. If some other client has already gotten access to the critical section, it means that it has permissions from at least a quorum of the servers via the master, and the next request that goes to the master will not reach a quorum, and it will wait until that first process exits its critical section. Now you could have failures here. If you have failures at the master, if the master fails, then you simply rerun the election protocol to elect a new master. If a replica fails, you simply replace it or it reboots by itself, and then have the new replica catch up with the other servers in the group or with the master itself. So Chubby presents a fault-tolerant way of not just doing mutual exclusion in a distributed system, but also to maintain small configuration files, which reflects the ways in which Chubby is used inside of Google's stacks. Wrapping up our discussion of mutual exclusion, it is a very important problem in cloud computing systems. There are a variety of classical algorithms. We have discussed four: the central, the ring-based, the Ricard-Agarwal algorithm, and the Maekawa algorithm. They're not all fault tolerant, but they are fairly efficient, and they all try to guarantee safety and liveness. And as we have progressed down from central to Maekawa, the algorithms have gotten better and better in terms of performance. Industry uses a variety of systems for coordination and for mutual exclusion. These include Chubby at Google, which is used for locking and also to maintain small configuration files, and also Apache Zookeeper, which is an open source system that is used for coordination. And I encourage you to look up Apache Zookeeper on the web.